Hello there. Today we're going to look at on the theoretical limitations of embedding-based retrieval. And this paper is really interesting because it proves something about embedding-based retrieval. So think vector databases in RAG and things like this. And the paper proves effectively that there are limitations to what can be retrieved. And this has a huge implications on basically all of AI nowadays, especially AI that works with any sort of data. Or so this paper would have you believe. The title is obviously very, it's a title that evokes certain feelings. It's a title that demands attention, like, whoa, we're all doing embedding-based retrieval nowadays, and there are limitations on it. I will make one change to the title that makes it more accurate and maybe much less impressive. The paper is on the theoretical limitations of embedding-based retrieval of random data. Now, we'll go through the paper and I'll explain to you what I mean, but effectively, the TLDR, and please watch the rest of the video, and it's really good for my stats, but the TLDR is if you have random combinations of data, then a certain embedding dimension is not going to be able to represent all of it. Wow. That was completely not obvious to anyone. This is so unexpected. In any case, I don't want to downplay the paper too much here. Like, it's one thing that, something is kind of obvious, and it's another thing to really rigorously go through and prove it and show it in experimental results and so on. But I just wanted to take away this expectation that this is going to mean anything for any practical application. It is not. It simply says random combinations have there, like, of a set of n elements, there are n choose two ways of making two sets, and you need the amount of dimensions to represent that. Otherwise, you can't retrieve a random two set. So, what are we talking about? For the people who are thoroughly confused now, what this all means, we're generally in the domain of information retrieval. And information retrieval is the following, where you have a whole, like a data set, let's represent it with this poorly drawn bucket right here. And in here are lots of, let's say, documents, right? In the internet, you can think websites. On your Dropbox, you may have, uploaded docs. It could also be pictures and whatnot, but we'll just take care of documents for now. So let's say these are documents, whatnot, Word documents, PDFs, text messages, and or websites in that case. And what a search engine does is it builds what's called an index, right? And an index is some kind of data structure that allows the search engine. So if the user over here, like EA, they have some search request, for example, I don't know, I want to know about the Paris Metro. Then we will go and consult the index, and the index allows us to very quickly retrieve data from this bucket right here. Why don't we go directly to the bucket? And that's because if there are a billion documents right here, then it takes really long time to go through all of them and check whether Paris Metro is in there. So we'll build an index. Classically, these index have been sort of reverse lookup tables. So I would start and I would have my entire vocabulary here. So I would analyze these documents, and as I do, I build up this vocabulary. So the word dog appears in documents number 1, 3, 5, 6, and so on. The word Paris appears in documents, 4, 8, 13, and so on. The word Berlin appears, and so on. You get the idea. So like in the back of a book, I have this index, and I can look up where the stuff appears. So if I search for Paris Metro, I will simply look up where Paris is, where Metro is, and I will take the intersection of those. So maybe Metro is in 6, 8, and 19. You can see that the document 8 is in both, so that's the document I retrieve. And now you can feel like if this is really a billion, then you'll get a lot of documents that have Paris and Metro in. So you need a way of kind of ranking that, and that's where typical, like very, very classic metrics like the best match 25 come in. This is a very common ranking technique. But this is not the topic of this paper, so ranking isn't. It's simply retrieval. Like, can or can you not, from this query, retrieve the relevant things from the database that match this query, and exclude things that don't match the query. Okay. Now, this is a sort of good old searching, and there is this new modern searching, which is embedding-based searching. So that's where you no longer have the documents and analyze the words in them, but you do have these documents. And from each of these documents, you create what's called an embedding vector. So you have some kind of neural network here, and you ship the document in, and out you get some sort of a vector. And here you ship this in, and out you get some sort of a vector. And now when your query comes, like Paris Metro, you also ship it into the same neural network, and you also get out a vector. And what you do now is you consider the inner product between those vectors. So these ones look pretty similar, so they go into the similar direction. And that's why this document would be more relevant than this document right here. What this paper is concerned with is, again, the same thing. So they have documents, they have queries, and they want to know whether it is possible for an embedding model to be so good at assigning vectors to documents and queries that for any given query, the relevant documents will be above the non-relevant documents. Cool. That's effectively it. If you go a bit further than this, then you'll know, okay, these are vectors, right? So they are, let's say, I don't know, what's a common embedding dimension? So let's say these are 1024 numbers, right? And they're always 1024, and you can make the inner product with these 1024 numbers right here. And we call these dense embedding models because all of these numbers almost will be non-zero, because these vectors they'll point in some direction. And the idea is that the vectors that point in a similar direction, they are similar somehow, they're related. And however, this here, and that might be not super obvious, is also a vector-based embedding. And you can also think of it like this. So the way to think of this is that your vector dimensionality is actually not like a 1024, but your embedding dimensionality is the size of the vocabulary. So your vector has as many dimensions as there are number of words in either your language or your corpus, depending on how you build your vocabulary. It is very uncommon for these kinds of indexes to use sentence piece or word piece tokenizers or byte pair encodings or anything like this, like we use in kind of large language models or frankly even these embedding models. So very uncommon, much more common to simply build a stemmed vocabulary of the whole language. So you'll have the vocabulary size as the embedding dimension, and then you simply, so for example, let's say this is the embedding vector for Paris. You'll put a 1. Oh, this is very... You'll put a 1 here, and a 1 here, and a 1 here. And this will be position 8, 4, 8, and 13. I cannot write numbers. And this goes on, right? Like this goes on for a long time because there are a lot of words. No, wait. No, this is wrong. This is wrong. Obviously, the vector is for a document. Yeah. Okay, the vector is for a document. So this here will be, I don't know, this here will be document number 8, right? So document number 8. And sorry about that. Yeah, you embed the documents. So the documents need to be assigned a vector. And so the document will have a 1 at the words that the document contains. So this here will be, you assign, so Paris here is the second word in the vocabulary. So at position 2, you have a 1. And then somewhere down, metro will be the, 94th word. So at position 94, there's also a 1. And there will obviously be other words in this document too. And these have 1s, and the rest is 0. Right? So we call these sparse embeddings because they're 0 almost everywhere, except at the position that correspond to the words that are contained in the document. You can go a bit fancier. If a word contains a document twice, you can put a 2 right here and not only a 1. But that's the general idea. And then you can do the same thing. You can do the inner product between two of these vectors, and that will tell you. So if the query is Paris Metro, right? So the query is over here. We do the exact same thing with the query. We put a 1 at the corresponding word. So Paris is here, Metro is here. And you can see that the inner product between those two will be non-zero because they do in fact have overlapping words. And the more overlapping words they have, the more non-zero it is, and the higher it goes. And you could even define other inner products rather than just the pointwise multiplication and summation that would correspond to various retrieval functions, such that all words need to be present or something like this. So what I'm trying to say is this here is actually also a vector-based retrieval. It's an embedding of type. Even it's a very trivial embedding, but it is an embedding and it is a vector-based retrieval, except that it's typically sparse, whereas this is typically dense. Sorry, this is a long preamble to the paper, but I feel it's important to kind of put everything here into perspective of that. Typically when we talk about vector-based retrieval, we think of neural networks and whatnot. No, it's kind of all just a matter of framing, right? And what's important here is that you can see that in the dense vectors, why is it different? And throughout this paper, it's going to be obvious. It's different because the number of dimensions here is so much bigger that it's much more flexible, right? You can represent any combinations of words being in a document, whereas this number of dimension is way smaller. And what that means is that you don't have as much flexibility to represent arbitrary combinations. And that's a feature of neural-based retrievers. But this paper here makes it into a bug. So let's go through the paper. It's a quick one to go through, I promise, because we'll kind of not follow along the math too broadly. But yeah. So they're saying information retrieval has moved from models dominated by sparse techniques, such as BM25, to those that use neural language models. That's what we just described. And what we're doing is we're predominantly using a single vector models, meaning that we take a document and then we produce a single embedding for the document. Now, I know, like, if long documents, you can chunk them and blah, 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 but that's implementation details, if you will. For now, consider one document is going to be one embedding. Even if we consider chunked documents, it does not change anything about the results right here. Now, the point of the paper here is that people have expected these neural models to solve increasingly complicated retrieval problems, to the point where people are effectively expecting miracles of these embedding vectors. They're saying even with the rise of instruction following retrieval benchmarks, where the models are asked to represent any relevance definition for any query. So the point of the paper here is effectively that now people are expecting way too much of these embedding models, to the point where they affect arbitrary instruction following, arbitrary retrieval. And the paper has a point. People do really expect miracles out of embedding vectors alone. And that's why you always see, if people are new to the information retrieval landscape, especially nowadays, they will often they will only exclusively use embedding vectors, which is already like, that's how you recognize a beginner. They will be like, okay, we're going to vectorize all the data, and then we're going to do nearest neighbor retrieval, and then that's going to solve all our problems. That's going to be magic. And that is definitely not the case. So the paper has a point that the expectation nowadays are too high, and with the instruction following retrieval even higher. However, the paper is going to rest their entire case here on this. The paper is saying, well, since people are now expecting more of these models, let's effectively prove that you cannot expect arbitrary things from these models. And to me, there's still kind of a disconnect between those two. Like, high expectations, I agree, they are too high. But the paper now says, well, we're going to prove that these models can't do arbitrary things, arbitrary combinations, right? Like it's almost a Gödelian argument. There are combinations of things that these models can't retrieve no matter what. But like Gödel's incompleteness theorem, this is completely pointless for any practical application. This, in my mind, this does not address proportionally the over expectations that people have of the models, which are still very much in line with what could be learned, but is just a bit outside of the sphere of what's possible currently. All right. So they're saying, okay, the Quest dataset uses logical operators to define different concepts and so on. Sure, that's really hard for embedding models if you have logical operators. So if you're not aware, if you search for something like this with embedding vectors, you're not gonna you may get actually stuff that has this, but you will also get stuff that has combinations of things. You will also get stuff that talks about two of these and things like this. And they're also saying, definitions of relevance by defining relevance in a way that requires reasoning. So yeah, if as soon as logic and logical reasoning and abstraction enters the problem, embedding vectors really aren't your friend anymore. And yeah, they push the boundaries of what dense retrievers are capable of. They're saying we seek to understand at a more fundamental level what the limitations are. Our work aims to connect known theoretical results in geometric algebra with modern advances in neural information retrieval. They're saying they get a lower bound on the embedding dimension needed to represent a given combination of relevant documents and queries. And they show that for a given embedding dimension, there exists top K combinations of documents that cannot be returned. Okay. Let's pause here and frame it like this. I have a set of elements, right? A set of elements. What you get two numbers to describe each of these, right? You can assign this one 1, 4, 2, 5, 9, 9, and so on. The mechanism to retrieve one is the inner product, right? You specify two numbers here, 1, 2, right? For example, 8, 9. I will compute the inner product and give you the element that matches. Can you retrieve any arbitrary element? The answer is yes, right? Because I can just always, if I'm like, okay, retrieve this one, my query is going to be 9, 9. That element's going to have the highest inner product. If you want to retrieve this one, my query is going to be 1, 4. That element's going to have the higher innerst product. This is trivial. Like, I'm not trying to trick you here. This is trivial. Now the crux comes. Can you retrieve combinations of 2 elements? Well, with what we see right here, let me see. I want you to retrieve these 2. Okay, maybe my query is going to be 2, 4, right? The inner product, this is not 24, this is 2, 4, right? Okay, the inner product here, well, it's okay with 1. 2 is better, right? 4 is going to match this and this quite well. Oh, sorry, I made a mistake. Well, not even. Right? You already see the problem. Actually, the 9 here, the 9 here, they're just gonna blow this inner product out of the water. Their multiplication are way high. So maybe we need some sort of standardized inner product, or actually cosine similarity between these. But yeah, that's my mistake. I'm sorry. So actually what I said before isn't true if we're simply concerning the inner product, right? Yeah, we want the cosine similarity, effectively just how similar the numbers are. What I'm trying to say is that as soon as it comes to combination of 2 sets of these things, then what you can do is, let's say I'm the adversary and I get to add elements to the set here to thwart the query maker's plans. What I can do is, let's say you hit exactly in the middle between 2, 5 and 1, 4 here, right? You put a query in that's exactly in the middle, so these 2 elements are closest to it. I can always put another element here that is closer to the query, right? And kind of makes it impossible to craft a single query that will hit both of these elements, but not this element here in the middle. So since we're 2 numbers, this is a 2-dimensional landscape, you can imagine this being spread out in the landscape. And it's just a matter of fact, if you do nearest neighbor retrieval in 2 dimensions, and you cannot craft your embedding so that you can retrieve an arbitrary 2 set of elements. 1 set, that works, but a 2 set, just combinatorically, you cannot retrieve arbitrary 2 sets. Do we need a giant amount of math to recognize that? No. Is this very obvious? Yes. Okay, you got the whole paper. The rest here is just math to find out exactly how many dimensions there is, which is interesting, but I hope this doesn't come as a surprise. Now, why is this not a problem for embedding-based retrieval? Because in embedding-based retrieval, the whole assumption is that there is a structure. There is a structure to the data and to the queries, right? So I want to retrieve Paris Metro because that makes sense. It makes sense to retrieve these 2 things together because in the data as a structure, cities have transportation systems and the metro is a transportation system and so on, right? Like, it's just the nature of language and the world means that there is a structure. And the whole point of embedding, the whole point of machine learning, the whole point of machine learning is that data and the world has structure. And we can learn this structure and we can use this structure to create a compressed representation. And by compressing, we give up certain freedoms. We give up the freedom to represent arbitrary combinations of elements in favor of having a more condensed and a generalizable representation. That's the entire point of machine learning. And this paper here is doing a lot of math and wording around the fact that, well, if you're doing machine learning, you're giving up. You're assuming a structure that you learn and thereby giving up the ability to make arbitrary combinations of data, to represent arbitrary combinations of data. Yes, that's the whole point. If I want to represent arbitrary combinations of data, I would just store the data, which is exactly what BM25 does, okay? Sorry. Again, the reason why this paper has absolutely zero practical consequence is that we use embedding-based retrieval in situations where the data has structure and where that structure is what we're interested in. And we're not interested in making arbitrary combinations. And yes, there are embeddings are now being pushed to things that they they're not supposed to be used for, but I don't think anyone seriously uses embedding-based retrieval to represent arbitrary combinations, and this paper is just hinging on that point, like, oh, look, you cannot make arbitrary combinations happen. I still feel like that it still does nothing practical. Okay, so two things happening in this paper. One, they're going to construct the data set. The data set is as follows. They are looking for name, like they have names, John, Ovid, Leslie, and so on. And they have things that one can like, right? Quokkas, apples, bananas, rabbits, candy, and so on. They're going to construct two sets. So John likes quokkas and apples. Ovid likes quokkas and candy. Leslie likes apples and candy, and so on. Okay, arbitrary combinations of two sets. And then they're going to show that an embedding, like if your embedding dimension is too small, you cannot represent arbitrary two sets here. You cannot retrieve arbitrary two sets with inner product embedding-based retrieval. Yeah, very obvious, but they construct the data set to show that, where exactly that point is where you fail to retrieve. On the other hand, they're going to theoretically show where that point is, and the two match up. And that's pretty cool. Like, if anything, like, I know I'm dunking on this paper, but that's pretty cool. Okay, so I will not go through the entire math right here. But effectively, the idea behind the math is to build so-called Curel matrices or matrices where it is specified that so the matrix is generally 0, except it's 1 if a document is relevant to a query. And then you can build another matrix, which is called the score matrix, and that's actually what your search engine gives you. And then what you want to do is you want to see that the two matrices are effectively equal, but not equal, but just that the ordering is the same within. So for every document, what you want is that the ordering of what you get out of the search engine is exactly representing the relevant documents over the non-relevant documents. And then they move to what's called the sign rank, and the sign rank is in the definition like the smallest integer d such that there exists a rank d matrix whose entries have the same sign as another matrix. And if you think about it a little, it's like these are not easy things to prove by any means. I could not prove them, so props to the math here. But in principle, if you can construct a matrix that has the same signs as another matrix, then there's an equivalence of that to the having a matrix whose ranks are as the relevance ranks are. So the sign rank defines the rank of that matrix. And so you might know that, for example, if you simply have one vector and another vector, you build the outer product of that, you get a matrix. But that matrix has rank 1 because effectively every row and column are just linear combinations of each other. So what that would mean is that your data has very a lot of structure, right? Effectively, a rank 1 matrix, like let's say you have two-dimensional space, but your data is all on one line. That's a one-dimensional data set, right? So if you wanted to represent this data, it would be rank 1 data, because all you would need to know is where on this line does a point lie, because you already know that it's not lying anywhere off this line. So that's rank 1 data. In higher dimensions, you can imagine the same thing. Now, the point is, the sign rank of this matrix here is effectively a direct predictor of how many dimensions you need to represent a given data set, right? Here, if I wanted to build an embedding model, I need one-dimensional embeddings, but as soon as my data set looks like this, I need two-dimensional embeddings. There are more complicated things than linear relationships, so if my data set looks like this, I also need one dimension. I just need to know, like, let's say the angle here from the top along this circle where my data is. But here we mostly care about linear relationships, which is fair in high dimensions. So really, like, this kind of data is really uncommon, except, I don't know, in geometric deep learning or something. So again, they're going to prove something about these things, and they ultimately, so if you look at things like this statement right here, where they relate the sign rank of a matrix to the ordering rank between what the search engine gives you and the actual relevance matrix, and that as a consequence they get out what they say here. In the context of a vector embedding model, this provides a lower and upper bound on the dimension of vectors required to exactly capture a given set of retrieval objectives. Practically, this means for any fixed dimension D, there exists a binary relevance matrix which cannot be captured via d-dimensional embeddings, as there are matrices with arbitrarily high sign rank. In other words, retrieval tasks whose QRL matrices have a higher sign rank are more difficult to capture, exactly for the embedding models requiring higher embedding dimension. So if you have more data and that data is of a more complicated structure, and the most complicated structure is obviously arbitrary combinations of two elements of sets, right? That is the most difficult thing you can do to a search engine, is like, how about you build a nearest neighbor retrieval index where I can retrieve arbitrary two sets of elements. That's the most difficult thing. More difficult than, like, you can adversarially construct even a data set like this. That's what they're saying right here. And that's, again, in a similar vein as in any formal system, there are statements that are true that the formal system itself cannot prove. It's a bit like that. Second, if we are able to embed a given matrix in a row-wise order-preserving manner, so if we're actually in a situation where we can represent a piece of data in a given embedding dimension, this implies a bound on the sign rank of 2a minus, this is the matrix filled with ones. In particular, this suggests a practical mechanism for determining an upper bound on sign rank of matrices for matrices via gradient descent optimization of free embedding representation. And this is interesting because the way they're going to the way they're going to experimentally show that their theory holds here is by saying, okay, let's define an experiment where the vectors themselves are directly optimizable via gradient descent. So the embedding model here, we don't train, we don't train the embedding model. We can directly optimize the vectors here, like directly. We have a data set of queries and of documents, and we just can directly gradient descent into these embeddings. So this has no relation to any training data or anything like this. We directly optimize the test set. So we are trying to overfit to a test set. However, the test set is this adversarial test set right here, where we have arbitrary combinations of two sets. And what you can already expect, and obviously what happens, is that as you increase the number of people who can like things and the number of things they can like accordingly, then it gets harder and harder for a given embedding dimension to capture all of the relationships here, even if you can directly optimize the vectors. Right? And that's what they do right here. And you can hopefully see in the graph here, the critical n value, where the dimensionality is too small to successfully represent all the top two combinations. So what they're going to do is they're going to pick an embedding dimension, let's say 25, and they're going to figure out at which n, so at which the size of data, can they no longer, with, no matter how they optimize the embedding vectors, represent this data. And that's going to be somewhere, somewhere. And then what they worry about is this relationship right here. And that relationship seems to be, in their case, of degree 3 for top two combinations. And that apparently matches the theoretical predictions in their case, which is pretty cool. Now, the critical n values for certain embedding sizes are, if you look at, for example, 1,000 dimensional vectors, you can go up to 4 million, and I'm going to guess n is the number of elements in this set, right? Of which you have to retrieve two things on, like two tuples, I guess, two sets. Sorry. And that critical n value is at 4 million, which I find crazy. I would have expected much less, but I guess it makes sense. You have 1,000 dimensions, but still, with 1,000 dimensional embedding, you can represent arbitrary combinations of two sets up to 4 million elements in a set, that's a lot. So even these theoretical limitations on a wild case that is adversarially constructed to make embeddings break, we still can represent 4 million things that accurately, right? Like without flaw. That's pretty cool. Now, obviously, in practice, you don't get to directly optimize the embedding vectors because you don't have the test set. But still, I would not have expected that. So then they're going out, and this is where it gets a bit more shady. Then they're going out and they say, oh, how about, real-world data set? And then first they hate on real-world data set. They're saying, oh, the real-world data sets typically use a static evaluation set with a limited number of queries, as relevance annotation is expensive to do for each query. This means practically that the space of queries used for evaluation is a very small sample of the number of potential queries. And yes, that is true. Retrieval data sets are notoriously small because you have to get a query, and if you want to do it correctly, you have to have them look at every single thing in the corpus and decide not just whether that's relevant, but how relevant in relation to everything else in the corpus that is. That's a giant amount of work. And even if you don't do that fully, still, annotation for retrieval is really, really hard to do and expensive. Now, what they're saying is, the space of queries is a very small sample of the number of potential queries. And that's where I have a bit of a quarrel, because again, I get that some people are expecting too much of embeddings, but it's not useful to want to do arbitrary combinations of queries. That's not a useful thing to do, because data isn't random, and retrieval intents, queries aren't random, and which data people are looking for given which queries isn't a random process, right? And it's not useful to evaluate search engine and retrieval quality on their ability to create random subsets of data. That's just not useful. Again, the whole point of machine learning is to assume the data has structure and to exploit that structure to be able to get away with compressed representations and gain generalizability. That's what we do, and not arbitrary Boolean combinations of things. They say, although it is not possible to instantiate all combinations when using large-scale corpora, search evaluation datasets are a proxy for what any user would ask for, and ideally would be designed to test many combinations as users will do. And then they say, oh, but that's not happening in practice. And that has a reason, because the users, as users will do, users do not ask for arbitrary combinations of things. Most people are looking for things that make sense to search for, right? And that is the same sense that the data has. And that's where I think this paper kind of falls off a cliff a little bit, is when they try to connect this too much to actual practical application. It would be fine if the paper said, look, we have a theoretical bound on like a combinatorics result effectively. Cool. And they can say, well, look, this relates to embedding retrieval in the following way. Cool. But the moment they try to make this about the practical implications of this, and they go after the benchmarks here, which are flawed, absolutely. And yes, people do expect too much of embedding vectors, but that's a bit too much. Yeah, so they have this data set, and this data set, obviously, current embedding models are terrible at this data set. Who could have guessed, right? And then they're asking themselves, is this domain shift? Or are we simply asking, you know, like, is it domain, like, are we simply operating in a different domain? Let's fine tune. Let's fine tune on a train test split of our data set, a train test split of random data. I'm not sure how this isn't, I don't know. Like, come on. Training on limit on the training set does not significantly help, indicating that the issue is not them. What? Yes. Like, I'm sorry, but I could have told you. And you knew this would happen. And that's a bit, I don't know, like, I get it. Like, this is paper writing, this is academia, but although our queries look similar to standard web search queries, no, they don't. They don't. Embedding models are not, they're not a database. Okay. And then they look at the correlation with MTEB. MTEB is a retrieval benchmark, and they're like, wow, look at that. There's no obvious correlation between how models perform on our data set versus how they compare on a standard retrieval benchmark. No crap. Because your data set is not testing any sort of practical retrieval capabilities. And yeah, so in the limitations here after the discussion, they say, although our experiments provide theoretical insight for the most common type of embedding model, which is single vector dense embeddings, they do not hold necessarily for other architectures such as multi-vector models. This is up to, we leave it to future work to extend our theoretical connections to these settings. I can tell you right now what's going to happen with multi-vector models. Your dimensions just have to go up. So if you have 5 vectors per document, then there is going to be a dimensions where they cannot represent arbitrary, probably 6 sets. I don't know, they might be, you might be able to get up to 5 factorial sets or something like this, but there's going to be a set number, like a number of combination and combinatorial things that you cannot represent because you simply don't have enough information available, like you don't have enough representation power. This isn't about how many vectors you have. This is simply about how many numbers you can play with and how these numbers interact with each other. And if you don't have enough numbers, you cannot represent arbitrary data with these numbers. That's the, I don't know. So yeah, that future work is possibly themselves writing another paper, and people again are going to be like, oh wow, ooh, I always suspect, I was always a bit I found these embedding vectors a bit suspicious. Cool, so that's 2 papers for the price of 1. And they say we did not show theoretical result for the setting where the user allows some mistakes, right? So like, what if you don't need to retrieve arbitrary things? You can make some mistakes. We leave that to future work. I can tell you what's going to happen, and that is you're going to get a bound that says if you are allowing for 5% mistakes, then your embedding dimension will have to be some function that's depending on those 5% larger, and then you cannot, and then you, with high probability, or absolutely, I don't know that yet. Absolutely, you can probably get you can very likely get an absolute bound on that. It's simply a bit of more math. The principle is exactly the same. The principle is exactly the same as here. So 3 papers for the price of 1. Anyway, that was it. Sorry, I know I was very negative on this paper. This paper is a solid paper. This paper, I have absolutely no doubt that the math is correct. It is explained well. It is written well. They do the exact experimental research that aligns with their theory. So they show that yes, indeed, their theory does hold when they put it to the test and all of that. My gripes with this paper is how they're trying to connect this to the quote-unquote real world and the sort of implications they make of it. And that is not necessarily a criticism to the people here, but more to the academic landscape nowadays, where if, there's a lot riding on you writing impactful papers, and the impact nowadays is much more on perception rather than actual content. So you can't even fault them for doing this because it might just be the landscape that forces everyone to make like put a cool title and connect it to the practice in a way that maybe not necessarily has this big implications. So I don't know. If I were a PhD student nowadays, I'd probably do this exact same thing, because this is going to decide whether you get a good job in a prestigious lab or not. If you're at a company like Google, this might decide whether, people who are PhD students want to come work for you. Like, you want the best talent, so you need the publicity. You need to show that you are at the forefront, that people want to come to you. So a lot is riding on this, with the rise of AI, and yeah, that's the times we live in. That's it. Sorry for being super duper grumpy. Yeah, thanks to the people who wrote this paper. I still appreciate it, and it's a good paper. And I would definitely accept it as a reviewer. That's it. Thank you. Bye bye.